The last topic we're going to talk about in this section is something called isomerism or isomers. And isomers are just amazing. You can have the same composition of a molecule, but have two different forms. And that's exactly what we just saw on the cis-trans. Cis and trans cisplatinum can have different effects in your body. Cisplatinum is actually good at fighting cancer, and transplatinum apparently doesn't do anything. So you need to have the right isomer in order to have the right reaction. Isomers are a huge part of chemistry, and we haven't talked about it too much in this class. In the Lewis structures, we saw some of the examples of isomers and how important they can be, but we're going to here briefly talk about how really important they can be in determining the composition and reactivity of certain compounds. There's many types of isomers, but they're all really important in both organic and inorganic chemistry. We're going to talk here briefly about what's called a coordination sphere isomer, a linkage isomer. We'll talk a little bit more about the geometric isomers, cis, trans, stuff like that. And then we'll get to the wildest one of all, which is stereoisomers. So get ready, sit back. This is a new type of chemistry, but it is actually a big part in an organic chemistry. You will definitely be talking about these in greater detail. A coordination sphere isomer is just fantastic. A coordination sphere isomer is two compounds. They have the same formula, but it depends where the ligand is bonded. Is it bonded to the metal, or is it outside, like balancing the charge? So let me show you two examples of this. These are both cobalt compounds, and they both have 5 ammonias. But notice there's a chlorine and a bromine. And in the first example right there, the chlorine is inner sphere. And what that means is that chlorine is connected directly to the cobalt. The bromide, on the other hand, is on the outside. So in water, like in the picture right there, the bromide would dissociate into bromide ions, but that chlorine will stick around. Now the second example, it's reversed. The bromine is connected to the cobalt and the chloride is outer sphere. So you put that one in water, you're going to end up with chloride running around while the bromine is connected to the cobalt. And these do create different reactivities, which is just amazing. So for example, if you add silver nitrate to both of those, silver ions love to react with bromide, chloride, and iodide. So with the first one where the bromide's on the outside, that silver will snatch that up to make silver bromide, which is quite insoluble. The chlorine on the inside is unscathed. On the other hand, if the bromine is on the inside and the chloride's on the outside, the silver will snatch the chloride like it does in the second one down there, and you'll end up with insoluble silver chloride. So you will get different products depending on where the ions are. They call these coordination sphere isomers. There's different ways sometimes to make one of those compounds versus the other. But again, notice same molecular structure, but because of where they are, the reactivities are quite different. Linkage isomers were honestly something that I didn't believe in the first time I heard about them. They were saying, like you see those pictures in the lower right, oh yeah, we've got different compounds, and the one was kind of an orange and the other one was kind of a rust color. And I thought, I said, oh yeah, you just oxidized one or the other and stuff, made it good. And amazingly, I was wrong. All right, well, not amazingly, I'm wrong. Actually, more often than I want to think, but amazingly, my initial instincts were incorrect, and I saw the research and I totally believe it. So let's talk about linkage isomers, because apparently they're real. Now again, linkage isomers, same formulas, all right? And these are showing some cobalts with a bunch of ammonias around them, but it's where the NO2 is connected that's fascinating here. So in the first one up there, you have a blue nitrogen right there, and the nitrogen is connected directly to the cobalt. So you can see in the left and the right, you've got oxygens. On the other hand, on the right side right there, it's not the nitrogen, but it's one of the oxygens which is connected to the cobalt. They call that the nitrito isomer. Well, when the N is connected, it's called the nitro isomer. And it does create different colored compounds. And again, I thought, oh, come on, man, this is silly. I thought for sure that maybe the nitro was oxidized to nitrate or something. I don't know. Anyway, I was wrong. I admit it. This is science. This is kind of cool. So yeah, this is a real thing. And some of these ligands, there's a choice where the metal connects. And I would have expected that the metal connected to the nitrogen, like the nitro, but sometimes they will connect to the oxygen, the nitrito version. And they do create different colors, different reactivities, all that jazz. Amazing stuff, but never say never in science. You just never know what's going to happen. A geometric isomer is what we've been talking about with cis-trans. It's again the same number of atoms and types of atoms, but it's the arrangement of them which makes a difference. Now, cis and trans becomes really important not only in organic but in inorganic chemistry. Mer and Fac is a special version when you have an octahedral system that's more relevant for inorganic, but it can be used in organic as well. So let's talk about how these things all work and what they mean. Geometric isomers are super important. We're going to see that cis and trans especially, the reactivities are quite different. Trans, we're going to see, usually means less polar, and cis means more polar. And anytime you have differences in polarities, you'll have different reactivities, different colors, all kinds of stuff. Fac and Mer, the other two, are also different reactivities. Not quite as drastic as cis and trans, but also important. So let's see what cis and trans is about, and as well as Mer and Fac. These are examples of inorganic complexes with cis and trans forms, all right? These are the cis platinums we talked about earlier. So on the left, cis just means 90 degrees. If it's a square planar like that, you'd have 90 degrees chlorine, platinum, chlorine angles. And that's going to be quite different reactivity-wise from the trans version, which means opposite. So the chlorines there are opposite the platinum. That'll be 180 degrees. The polarity of that will be quite less than the cis form. And sometimes, like in fighting cancer, the cis form is more reactive and more active than the trans form is, so they need to have just the cis form to make it happen. You can also have cis and trans in octahedral compounds. Cis just means, again, close to each other. So you can see on the left-hand side there, you've got that kind of purple compound with cobalt. The chlorines are cis. They're at 90 degrees. On the other hand, on the right-hand side, those chlorines are opposite each other, 180 degrees. And you can see there's quite a difference in the color. It's more of a green kind of color. So cis and trans, again, creates different colors, be different reactivities. The trans version, I would argue, is almost completely non-polar, while the cis version is quite polar. So you'd need the different kinds of solvents and chemicals to react to make them work. Fac and Mer are sometimes used for octahedral compounds. And in a Fac isomer, notice how you have one trans 180 degree angle between two of the atoms. So what I just highlighted right there, that was two of the ammonias that are 180 degrees around octahedral. And you also have, in this case, because there's 3 and 3 of the atoms, you also have 180 degree green atoms, chlorines, whatever, that are 180 degrees. So Fac systems that have two trans pieces like that, two 180 degree reactions, generally are less reactive, all right? Because the things I just highlighted there, all of those are basically non-polar. It's only the one green Cl and NH3 in the middle there that I didn't line up. Those would be the most reactive and most polar things. Now, that being said, the Mer version, on the other hand, everything's at 90 degrees. There's no chlorine, cobalt, chlorine 180 degrees, which we had on the Fac version. If you have everything at 90 degrees, you're going to have a much more polar molecule. So generally speaking, Mer isomers are more reactive. They're more polar than the Fac isomers. Fac isomers are still polar, but not as polar as the Mer forms. So if you see Mer and Fac, you know now what it means. Optical isomers are a wild trip, and this is the one that's kind of hard sometimes for people to wrap their brains around. Optical isomers are a good reason that if you ever take organic chemistry, you must have a model kit, all right? It's just so important because optical isomers can be kind of weird to see. If you think about your hands, your right and your left hand, they both have 5 fingers, one thumb, one pinky, one index finger, etc., etc. But they're not the same. Like they're almost like if you put your hands in front of you, it's almost like you have a left and a right hand or a mirror between your hands that's showing the opposite one right there. So optical isomers are just two molecules, same form, but they're almost like looking at a mirror at each other. And if you try to put them on top of each other, they're actually different. In the middle part of that lower diagram right there, it shows isomer 2 on one side of the mirror and isomer 1 on the other. And looking at each other that way, it looks like the same molecule, just like your right and left hands would be. However, if you can do this in your mind, cool. If you can't, I'll show you something in a little bit. Imagine that the white atom on top and the blue atom kind of sticking out at us were aligned, all right? And if you do that, you can move isomer 1 just a little bit to the left. Notice that the yellow atom would be on top of the pink atom, and the pink atom would be on top of the yellow atom. So they are like our hands, all right? You can't superimpose them. So optical isomers is a newer part of chemistry. And if you have two isomers that are chiral, that means that they are actually have these hands. They're like left and right hands. And they're sometimes referred to as enantiomers. So some molecules will be chiral. They'll have a left hand and a right hand, or two different enantiomers. And oh boy, if you have an enantiomer, you can be definitely signed up for some really wild chemistry, which sometimes doesn't make sense. Here's a picture of your hands on the upper part right there. You can see how the hand looks the same, left and right, but they're not the same. You try and put them on top of each other, and of course they're not going to be the same. And you flip one hand around, and then the thumb is by the pinky, pinky's by the thumb, etc., etc. It doesn't work. Well, this is something that happens in chemistry as well. So in the lower right-hand side, we have two molecules which look like they're on opposite sides of the mirror. And if you try and superimpose them, that's not going to happen either. So this would be an example of a chiral molecule. If you have a tetrahedral molecule and everything around it is different, for example, a chlorine, a bromine, an iodine, and a hydrogen, then you're going to have this chiral behavior, and you'll end up with like a left and a right hand enantiomer, and that's when you have to think about all these crazy things. These optical isomers and enantiomer do possess a lot of identical properties, and this is what makes them really tough. Enantiomers will have almost identical solubilities, melting points, boiling points, colors are the same, chemical reactivity, as long as it's with non-chiral things, all of that stuff is the same. So you might go for a long time without even realizing you had one of these optical isomers running around in your system. However, if you place these enantiomers in what's called plane polarized light, you'll be able to see the difference. And even worse, or better, depending how you look at it, if you take your chemicals, which are enantiomers, they've got a left and the right, and you react them with other chemicals which have a left and the right, you will see differences in reactivity. If you take a light from a normal source, the light comes out in 360 degrees all the way around the light. That's what they call unpolarized light, and you got light in all different variances and stuff like that. Well, you can place the light through what's called a polarizing filter. And in a nutshell, what a polarizing filter does is it creates a plane of light. They call it plane polarized light. So you can see in the first part there, the unpolarized light, that's all over the place. But once you get to plane polarized light, it's just like two dimensions, all right? It's going up and down, but only along that axis, which is kind of cool. So you can create polarized light from regular light if you have the right equipment. It's not hard to do, and it can be really helpful, as we'll see in this example. So if you have the plane polarized light and you place it through a solution of the one enantiomer, not both of them, but the one of them, you will see that plane polarized light rotate. And this is just wild. They can rotate to the right or the left. And so as an example, let's say that we have just the one isomer, it might go to the right 32 degrees. And they call that, by the way, dextrorotatory. D, you don't need to worry about that. Anyway, the other enantiomer, if you did the same thing, it would do the same process, the same angle, but to the left. So it would be to the left 32 degrees, and they call that levorotatory, and they get L. So anyway, these crazy enantiomers will rotate your light. This is how they figure out that that's there. They can be to the right or the left. It'll be, as far as I know, the same angle all the time. And again, you have to have a pure enantiomer. Like you have to have just the right or the left to make this happen. Can't be both. So if you see the little called D or L, that just means it's rotating this plane polarized light to the right or the left, which is incredible. Now, if you do happen to have both of them, you have what's called a racemic mixture. And a racemic mixture means you have equal amounts of both enantiomers. So like half of it would rotate to the left, half of it would rotate to the right. You don't see any rotation. So it's very difficult. You have to have pure enantiomers, and you send this plane polarized light through it, and it does make the light go left or right. Pretty crazy. But again, by default, you might have a racemic mixture and not even know you have one, which is just crazy. If you know you have an optical isomer and you've seen that you have left and right, you will have different reactivity if you use other reagents, other chemicals, which themselves are chiral, like you'll have a left or a right-hand version. And it's, again, just amazing that this can happen. Sometimes you can even have a racemic mixture, like both left and right, and if you add the right reagent, you'll extract, say, the left from the right. This is a really wild part of chemistry. So this is an example I found online. In this example, we were unable apparently to separate our cobalt compound from the left and the right, from the D and the L, the dextrolaboratory, et cetera, et cetera. All you need to know is that's a mixture of left and right. So if you add a chiral reagent, the D version right there of that thing, the D version reacts with the D version in the racemic mixture, and it makes a solid. On the other hand, the D totally ignores the left-hand version. You can see that it stays in solution and doesn't do anything. Well, hey, if you got a solid, you can filter it out, decant, all that kind of stuff, get it away from the other one, the left version. This is how they can sometimes separate these things, which is just crazy. But again, first you have to identify that you have a mixture and the possibility of chirality before you can apply these kind of things. In our recent past, sometimes these left and right enantiomers have both been present, and people didn't know they had a left and the right-hand version, and it created different results. Ritalin was used for kids with ADHD, and apparently Ritalin has a left and a right version, and the one version is really helpful, helps to kind of make people more chill and stuff like that. The other one, though, kind of makes them nervous and stuff, so they're figuring out how to separate those out, which is cool. Thalidomide was a chemical given in England in the 1950s to help pregnant mothers. Well, unfortunately, thalidomide had a left and a right-hand side as well. The one side was beautiful. It helped them out a lot. On the other hand, the other side was really bad, and kids were born with birth defects, stuff like that. There were huge legal lawsuits. So anyway, just realize this is a cutting edge of chemistry. It is complex, but it's all stuff that can be done. As we develop this technology more, it will get easier to not only identify, but separate them out. Pretty cool stuff.